Okay, let's start. Do you have any questions? All right, so I guess the plan today is first, let's take a look at a few of the questions assigned for last homework. And then, so this is homework, right? 7, homework 3, right? And then we'll look at conditional expectation. And then we'll look at law of large number and central limit theorem. So that's quite a lot of things to cover. So we'll, I guess, try to see how much we can do. But yeah, of course, right, I'm not gonna go over every single question here. The solution, right, will be posted on, later on tonight, so you can take a look at the details. Let's see, which one do I want to yeah. So maybe let's take a look at the first one, which is 7.3, right? So it says gambles are independent. Each one results in the player equally likely to win or lose 1 unit. Let W denote the net winnings of a gambler whose strategy is to stop gambling immediately after the first win. Okay. And then find A, probability W is positive, B, probability W is negative, and C, expectation of W. All right. So this question is not super special. The only thing is to understand, right, what they're asking, which entails understanding what W is about, right? So let's see here. It's very easy to misread W, right? To think that because the strategy is to stop gambling right after the first win, it's easy to misread W to be 1, right? With probability 1. Because you're gonna win 1 unit, right? And so the answer here is 1, 0, 1. Is that correct? Well, the answer is no, right? It's not correct. Why? Because W is not the winning at that point, right? When you first win, W is the net winnings, which, rather you can just say the total, winning or total gain loss, whatever you want, right? Basically, it's the whole, right, trajectory, right? The whole sequence of win loss, right, until the first win, which of course, right, really when you think of it, means what? Because it's the first win, that means that before that, right, the gambler must always loses and then win, right? So if you take a look at that, this exactly is the whole sequence, right, is a geometric 1/2, right? The number of gambles, the number of games. So net winning, right? If you let X be a geometric 1/2, then the net winnings will be what? Minus of X minus 1, right? And plus 1. Agree? Which is 2 minus X, right? And so probability W positive is probability X is less than 2, which is probably X equals to 1, which is a 1/2. Probably X is W is negative is probability of X is bigger than 2, right? Which is 1 minus probability X is equal to 1 or 2, which is 1 minus a 1/2 minus a quarter, right? Which is a quarter. And the expectation of W is 2 minus expectation of X, which is 2 minus 2, right? Which is 0. Okay, so far? Any question? Okay. So let's look at 7.9. It says this. There's a total of n balls numbered 1 to n, right? And they're put into n urns in such a way that ball I is equally likely to go into urns I 1, 2, etc. up to I. Fine. The expectation number of empty urns, and 2, the probability that none of the urns is empty. Okay. So how do we do this?
You let xi be the probability that an urn is empty.
Yeah, okay. No, I mean, you probably want xi to be 1, right? And then, yeah,
Yeah.
if urn I is empty, okay, 0 otherwise. And so expectation of xi is probability of urn I is empty, yeah, which is what?
I over n, or empty would be 1 minus I over n, I
All
believe.
right, so yeah, it's 1 minus probably xi equals 0, right?
Yeah.
Which is probably something is earned in urn I. Wait, hold on. Say that again. It's 1 minus I over n. Is that what you said? Okay.
Yeah.
What's the reason? Why is so x equal to 0 means the pro x equal to 0 means says something in urn I, right? So
Um,
you claim that that's I over n. What's the reason?
yeah.
I think this might be correct, but what's the reason? Why is it the probability something is in urn I is I over n? I mean, how do you do that calculation? So first of all, right, this problem has a peculiar structure, right? That ball I is equally likely to go into urns 1 to I, right? Now, usually it's equally likely to go into urns 1 to n. I mean, doesn't have to, but that's how it usually reads. So there's a small chance this is a typo, but you should just respect, right, whatever the prompt says, unless it's really weird. But it's 1 to I, right? What does that mean? That means that ball 1 is guaranteed to go to urn 1, right? So guarantee. For ball 2 can go to either 1 or 2. Ball 3 can go to either 1, 2, or 3. So on and so forth. Do you understand? And so just with that structure, is it easy to come up with this I over n? That's just what I'm curious about. So what I think, right, is that, so let's bracket this. Is to look at this, right? I mean, what does it mean for an urn to be empty? That means no ball, right, goes into it, right? And how would no ball goes into it? I mean, well, so no ball goes to it means every single ball will miss it, right? So some kind of product, right, of probability, let's say ball K does not go into urn I, right? Where K goes from 1 to N. Agree? If no ball goes, and then the product is because clearly the balls are independently, right, going to the urns. I mean, the action of the balls itself, right, does not affect each other. Agree? Now, what is the problem ball K does not go to urn I? Now, if you notice, right, the peculiar feature is that, of course, if K is less than I, for example, urn 4, right, then ball K is guaranteed, right, not to go to urn I, because ball I's only go to urn I. So if K is less than I, ball K will not go to urn I. Okay, so far? So the product here must start from I, right, up to N. Okay. Now, if starting at I, what's the probability ball K does not go into urn I? So it's uniform 1 to I, right? Uniform 1 to K, rather. Sorry, right? K is the index of the urn. So it's K minus 1 over K. Agree? Because it has to miss exactly that urn. Okay, so far? And then that would be what? I minus 1 over I times I over I plus 1, etc., right? The last one will be N minus 1 over N. Right? And so you see this is a telescoping product, if you will, right? And so the final answer, right, is, so actually here, my calculation will come out to be I minus 1 as the whole thing over N. It's not, yeah, it's not this, right? It's not N minus I over N. It's I minus 1 over N. Is that okay? Any question? And that's just, is that the answer here now? Oh, right, because now we have to sum up over xi, right? So the answer for A will be sum of the expectation of xi, right? Which is sum. But whatever that is, right? You can write down the, n times n plus 1 over 2, blah, blah, blah. We don't need to simplify this. We can, but whatever. All right, any question? In some way though, right? This one should remind you, yeah. Go ahead.
Sorry,
I don't think I can. I'm not sure I can hear you completely, so
Oh, is it first?
say that again.
Can you explain why you changed the bounds from k equals 1 to n to k equals I to n?
Because here, ball I can only goes to urn 1 to I. So if you're at urn 4, for example, then balls 1, 2, 3 will completely miss urn 4. Right? So ball K, if K is less than I, will not have a chance to go into urn I. So it's 1. It's guaranteed. You don't need to multiply it.
Okay, thank you.
Again, right, this is a small thing, right? It could have been an N, but these will be completely two different calculations. And if you take a look at your textbook, it's I, right? And like I said, we have to respect that. Yeah, so what I was saying is that this sounds a lot like the hat problem, right? The gentleman exchanging the hat, except that it has some subtle difference, right? Of course, the first thing is that two balls can, you can, if you look at the ball as a hat and the urn as a gentleman, then there are two crucial differences, right? The first is that ball I can only go to urn 1 to I. But the second thing is that two balls can go into one urn, right? Meaning one gentleman can pick two hats, whatever that means. But in the hat problem, each gentleman can only pick one hat, etc., etc., right? Anyway, so part B, because the reason I mentioned this is like part B sounds a lot like the hat problem, right? Probability none of the urns is empty. So how do we do part B?
Wouldn't this require that every ball goes into its numbered urn, like ball I goes into urn I?
Yeah, that's exactly correct. So here, right, for part B, so I'm saying this, right? If you think about it and if you kind of work it out, let's say using formula and stuff like that, then if you remember, right, this is like a classical inclusion exclusion formula where the probability of the urn is empty, right, is 1 minus the probability that some of the urn is empty, right? Because, and then the probability some of the urn is empty is a union, right, overall. And then you do an include and exclusion, which is exactly the approach used in the hat problem. But because of the 1 to I here, if you use inclusion exclusion formula, it's going to be pretty tedious to write down the intersection of xi, xj, xi, xk, etc. Okay. So what I'm trying to say is like, hopefully you do think of inclusion exclusion formula here, even though it's not, let's say, the right approach in terms of how much you need to write. The reason, right, is because again of this structure right here, right? But you want to think backward. For example, if none of the urn is empty, that means the last urn, right, urn n is also not empty. But how could the last urn not being empty, right? So you kind of do like this. Go back to urn 1. Urn n not empty only when ball n goes into it. Because no other balls, right? No other balls can go into urn n besides ball n. That's the structure. So ball n must go to urn n. But if ball n goes to urn n, then the only thing available for urn n minus 1 is ball n minus 1, right? Or if you will, right, condition on the event that ball n goes to urn n, then the only thing, right? Because notice, if you just separate this event out, then either ball n or ball n minus 1 can both go into it, can go into it, right? Because either way. But if ball n has already been forced to go to urn n, then the only thing left is ball n minus 1 to n minus 1. And if you carry that out further, then that's ball n minus 2 going to urn n minus 2, etc. So does it make sense? It's probability that ball I is in urn I. Multiply with the product. And by the way, right, this is not the product of these things. Meaning these guys may not be independent, who knows, right? They're not independent for sure, because this influences that. The product here is the independence over the ball I, right? Action of the ball I, okay? So, but these two statements are equivalent. And so then, and then use independence on the ball I. But then this will be what? The product, right? And ball I is in urn I with what kind of probability? I minus 1 over I, right? Wait, am I right?
Shouldn't it be 1/i?
Yeah, because otherwise we zero. Thank you. Yeah, sorry. So it's actually 1 over n factorial, right? Okay, any question about this? All right. So I think there's a follow-up question here somewhere, right? Question 7.32. Where they ask for, in the above question, right? Compute the variance of the number of empty urns. So how do we do this? Well, so you see, right? The xi here is 1 if the number of urns is empty. So I guess we skip one thing here where we, right, just define x to be the sum, right? So x is the number of empty urns, correct? So here, they ask for the variance of x, which is the variance of the sum of xi, right? And this is a classic problem where there's nothing much you can do besides using the variance covariance formula, meaning that this is a sum of the variance of xi plus twice sum of I less than j, covariance of xi xj. And then you just have to compute each of the terms here. Now, in some cases, right, the total sum here simplifies to something. But the expectation here, I mean, expectation in terms of not math, right, just expectation of your work, is not for you to simplify this, but for you to basically spell out these guys correctly. Whether it can simplify or not, let's say that we don't really worry about now. Okay? So we only need to write this down, and then we'll go. Let's say so. I mean, ideally, you should pay attention to see if these guys are equal. Because if they're equal, I mean, I'm not saying this is equal to that. I'm saying these are equal among each other. Because if they are, then it's just n times some number. And if they're equal here, then it's 2 times n choose 2 times some number, right? Things like that. But beyond that, usually there's not really a lot of simplifications. So what's variance of xi? So the xi is Bernoulli, right? So variance of xi will be P1 minus P. Which is that number we found times 1 minus it. Because this is expectation of xi, right? Again, probably there's no need to simplify this, right? What about the covariance? So the covariance, right, will be expectation of the product minus the product of the expectation, right? Now, this will be I minus 1 over n times j minus 1 over n, right, as calculated above. What about this? So remember, right, the product of two indicator functions will only be 1 if both of them are 1. So this is probably xi equals to 1, xj equals to 1. Okay. Meaning that the probability x earn I is empty and earn j is empty. How will we do that? So again, right, just do it directly. This is the probability that no balls, right, going to earn I and earn j, right? How would that happen? Well, so here, right, again, this is actually where things get a little bit hairy because of the structure, right? That ball I can only go to earn 1 to I. Because, right, for example, right, we already careful to write I less than j. So for I less than j, first of all, right, for any k less than I, they cannot go to either I or j, right, the ball, right? So maybe let me just write down. This is the same as probability, right? That ball k does not go into earn I and j, right? This is a product of all k's. All right? I mean, I'm just looking at this. This is the same. Which is product, right? So first of all, it only counts up from I because below I, right? Ball k is guaranteed not to equal e to either I or j, right? I less than j. So, but if it's between I and j minus 1, then it can only go into earn I, not earn j, right? So that's going to be I minus 1 over I. And then from j to n, it can go into either one. So it's going to be, sorry, this is k minus 1 over n. Okay. And this is k minus 2 over k. And again, these two are just whatever. So we don't, I mean, you can simplify them, but I don't know. I mean, you can definitely simplify this. The k minus 2 over k structure seems a bit not nice. I mean, not nice. It's nothing really cool to simplify. But that's it, right? And you just plug in. Who knows if it simplifies to whatever, and we don't care for that. I mean, at least we don't want to spend time investigating that. Any question? All right. So I think let's take a look at the last question here. Well, two more questions. So the first one, is 34, right? 10 married couples are randomly seated at a round table. So that's easily missed, right? I mean, if you just read a question, it's a circle, right? At a circle. And they say compute A, the expected number, and B, the variance, so expectation and variance of the number of wives who are seated next to their husband. Okay. And it's just a comment here. It's a bit peculiar the way they word the statement, because what's the difference between that and couples sitting next to each other, right? Because if the wife sit next to the husband, that means the couples are sitting next to each other, and vice versa. So, but I think maybe, just maybe in the context of a round table, somehow saying it like this is a little bit easier to think of the arrangement. Who knows? But this literally, right, is the same as couples sitting next to each other, I think, right? Anyway, but how do we solve this question? So again, right, you let xi be 1, right? If, let's say, the I couple, right, are next to each other, right? Zero otherwise. And you're looking at x, which is the sum of xi, 1 to 10, right? And you're looking at expectation of x and variance of x, right? And expectation of x, of course, entails expectation of xi, which is what? What's the expectation of xi here? which is of course a probability xi equals to 1, right? Meaning that the probability that couple I next to each other, which is why.
2/19.
That's correct. Right, so it's really 20/19. Okay, so how should we justify, right, this answer? So a round table, right? I'm not sure if that's a easy, not easy, but a different way to think about it. Whenever I see a round table, to me, what it means is one person, right? A position of one person is irrelevant, meaning that you can put that person anywhere you want. And then the remaining, right, would make a permutation, right? And the selection of that person doesn't matter either. So two ways you can think about this. You can pick, when you look at xi, because it's really about wife slash husband. I mean, it's not, but if you kind of focus on the husband I, and you pick that person as the anchor, right? Then for the wife I to be next to the husband, there are two positions, right? There are two positions out of 19 left, right? So that's 2/19. That's one way to think about it. The second way is to choose the anchor as someone not the I couple, right? So not the I couple, right? So again, right, there's 19 position left, right? So that's 19 factorial. But out of those 19 factorial, right, you must, this is the one we did it before, right? Yeah, 18 factorial ways, right, for the two couples to sit next to each other times 2, because you can permute them, right? And if you check, that's also 2/19. So either way, right, you can argue it out. That's 2/19. All right, any question? All right, so for the variance, right, it's really just about the variance covariance formula, right, which is the sum of the variance plus 2, right, sum I less than j, covariance of xi xj, right? And hopefully it's easy by now that the variance of a Bernoulli is P1 minus P. Where is this? So it's 2 times 17/19 squared, right? And then times 10, because they're all the same numbers. Covariance of xi xj is expectation of xi times xj minus expectation of xi times expectation of xj, which, right, this one is 2/9 squared, right? What about this? This again, right, is probability that xi goes to 1, xj goes to 1. What is that? What's the probability that the I couple and the j couple are next to each other? So here, right, notice that it will be the same as this argument, but it's easier if you choose this approach, meaning choose someone, not the I or the J couple, right? Because you can choose anyone to be an anchor, really, right? So again, there'll be 19 factorial ways to arrange the remaining, right? But out of that, we have 17 factorial, right? And then 2 square way to make sure that these two couples are next to each other. So that's that, right? 2 square over 18 times 19, right? And again, these numbers are the same. So you have something like 10 choose 2 times that. And I think these numbers simplify to something, but I'll leave it for you to figure out. Any question?
Could you also do like conditional probability for the probability xi equals 1 and xj equals 1?
Haven't thought of that. So you want to do it like this, right?
Yeah.
And this is 2 over 9. Condition on the one couple being next to each other. What's the probability other couples are next to each other? So basically you have 2 units apart already, and you want to look at the remaining ones. I'm just trying to think in a circle, conditioned. You know that the other couple is already next to each other. So you would have something like 18 factorial, and then you look at, so it's basically the same way of counting, right? But instead of 9 factorial, you would have 18 factorial. So you're referring to?
Yeah, but I think you could also think of it as like 2 over 18 times like 1 over 17. Like if you would just look at like
Oh, you just look at like
if
oh,
you
I
like
see.
pick one
Yeah,
couple,
yeah. You do the other way of counting where the wives have
Yeah.
2 positions. Right. Okay, that's why you condition, because that would, yeah, because I was just doing commutative, so I don't see the benefits of that. Yeah, I can see why. Yeah. No, yeah, I mean, it's valid. It's valid. It's valid. Yeah, as long as you can see a way to use the conditioning beneficially, then yeah, I can see where you're going with that.
Okay.
As long as the answer would be the same as this. Yeah, cool. Yeah, that's correct. Any other question?
Is this supposed to be, why is it 2 over 9? Not 19.
No reason. I was just zoning out. Thank you. All right. Okay, last question here would be what question was it? Oh, 7.39, right? So quiz 5. So 2 balls are removed randomly, right? From an urn containing N red and M blues. So xi is 1. So yeah, if the ith ball removed is red and 0 otherwise, right? You just look at these 2 balls. And so they ask you to first to consider this, right? Covariance of xi, xj. They ask you to first think about whether it's positive, equal to 0, or negative, and then justify your answer. And justify here, of course, is just calculate out, right? No other way. So I guess, of course, it's probably just a routine question to calculate covariance, but it probably tries to encourage you to think of covariance intuitively to see if you could guess the direction of covariance. Whether or not the exercise is helpful or not is up to you to think about. But so, what do you think here? Would they be positive, negative, or 0? And the sign of covariance, right, is the same as the sign of correlation. So if you find covariance not familiar, you can think of correlation, because in terms of sign, they are the same. Are these two negatively correlated, positive correlated, or have 0 correlation? Again, right, there's no right or wrong answer when you have to try to guess something. It's just basically building your intuition. I would go with this, okay? The reason is because, just some sort of like rule of thumb, right? If this guy increases, one of them increases, what's the effect on the other one? Again, I'm not trying to say it's a cure-all, whatever. It's just some question you can ask. And it seems like, right, again, all these are subjective. If it seems like if one of them is red, it decreased the chance of the other one being red, right? So that's why it seems like they're negative. Again, it has to be justified through calculation, but mine saying the negative is because of that. If there's another intuitive reason that you feel will be better here, feel free to say it. But let's see if that's true, right? What's covariance of xi, xj? That's expectation of xi, xj, right? Minus expectation of xi, expectation of xj, right? And expectation of xi, meaning that the ith ball removed is red, that clearly will be, right, n over n plus m squared, right? And this means both of them are red. And that's just the hypergeometric, right? So n choose 2 over n plus m choose 2, right? Okay. Which is n times n minus 1 over n plus m, n plus m minus 1, right? Like that. And you have to do some work here, right? Which is not that hard. Factor out n over n plus m. You have this minus that, right? And if you do common denominator, n minus 1 times n plus m, I'm running out of space here, right? N minus 1 times n plus m minus n plus m minus 1 over n plus m minus 1 n plus m, right? And if you look at this, there's n squared minus n squared, that's cancelled. There's minus n. There's a plus n, so that's cancelled. There's a plus nm. There's a minus nm, so that's cancelled. But there's a minus m here, right? That's not cancelled with anything. So final answer here is minus nm, right, over this. Of course, this is the value, but we care for the sign more here, so it's negative. So it seems like the intuition is correct, right? But who knows, right? So that's the answer here, right? Again, I'm guessing it because I'm thinking that one of the ball being red will decrease the chance of the other ball being red, if you know, right? But I'm thinking about it, I'm not so sure if that's right, because maybe, who knows, right? Because because you sample without replacement, right? Basically, if one ball is red, sure, right, you will decrease the number of reds here, but you also decrease the sample pool. So it's an effect on both numerator and denominator. So, yeah. Well, actually, you know what? I think I'm still okay. Anyway, again, this is subjective. But what I'm saying is, like, if you have two balls out, right? And if you see that one of them is red, probably, right, the other one would be less chance of being red. Or conversely, if you see one of them is blue, not red, right, then you would guess that the other one chance of being red is higher, sort of intuitively. So again, right, covariance is not an easy object to intuitively guess because it has to do with linear correlation. So the reason, right, is part B says that now the balls are numbered. The red balls are numbered. And yi is 1 if the red ball I is removed. So you see, it's more specific here. Before, it's just the first red ball, right? The first ball being removed is red. Then that's 1. Here, the first ball being removed must be the first red ball, or the red ball number 1, right? Then it's 1. So that's the difference. So now they ask you, right, again, whether this is positive, equal to 0, or negative, and then justify, meaning calculate out, right? So what should it be here? So here, I guessed 0. Based on what? Based on because the balls are numbered. Therefore, one red ball being removed does not have an effect on another red ball, particular red ball being removed. Okay, it's a chance. But let's see if the calculation justifies it, right? Again, it's expectation of y1, y2, minus expectation of y1 times expectation of y2, right? But notice now the balls are numbered, so it's a particular ball. So each of these is 1 over n plus m, right? Well, y1, y2. That means both of these are removed. So here you have to, I think the answer is like this, right? There's only one way for both of them to be removed, right? Because they're particular balls. The denominator is still a n plus m choose 2, right? Overall. Yes. So that's the covariance. Okay. So which is what here? This is going to be 2 over n plus m times n plus m minus 1, right? Minus 1 over n plus m squared. Which will be, right, again, right, 1 over n plus m times 2 over n plus m minus 1 minus 1 over n plus m, common denominator, 2n plus m minus n plus m minus 1, n plus m, n plus m minus 1. And if we look at this, right, we got 2n minus n, which is n, 2m minus m, which is m, and there's a plus 1, right? So actually it's going to be something like n plus m plus 1 over n plus m squared n plus m minus 1, which actually will be positive, right? And of course, that means that my intuitions are wrong. Right? It should be this. And again, like I said, who knows, right? You just, this is meant for you to just check your intuition. But the ultimate thing is to calculate out, right? And well, why should they be positively correlated? Well, so let's try to see if we can see it. So again, right, it probably has to do with the balls being removed without replacement, right? Without replacement. So if ball I is removed, if the first red ball is removed, then purely, right, it will not change number of red ball remaining. Then, you know, there's still the second red ball remaining, but the sample size removed is smaller, right? Because you have removed one ball. So in that sense, I think if the first red ball is there, then it increases, right, the chance of the second red ball being picked, right? But the difficulty with that interpretation is that if the first red ball is not picked, meaning it's a blue, right? So if it y1 decreases, right, from 1 to 0, then it still seems like the second ball, the chance of being picked will be higher, because either way you remove, right, you remove a ball out of the sample, right, and you don't affect how the second ball is being removed, because either the first red or, okay, hold on, I think that's wrong, right? If it's not the first red, then it might be the second red. Maybe you picked the wrong one. Then in that sense, it might also decrease the chance. Either way, all I'm trying to kind of say is that at least it seems to me covariance here is not that. I think if for me, the message here is that covariance is not that easy to say straightforwardly that it got to be positive, negative, or 0, right? You may think so in some cases, maybe. But overall, I feel like this object is a little bit complex in terms of the sign, right? So it just tells you that correlation, as far as I think, may not be easy to guess a sign in cases. So you have to calculate out. Anyway, any question? All right, so now we're done with the homework. So in terms of the topics I want to go over, right? And here, of course, it's just going to be gone over in the sense of introducing you to the topics, etc. Right? We're not going to do problems on it, so probably you won't get an in-depth treatment here. But you will see more of this probably in statistics, this in stochastic process, for example. So, you would get more training there. But in terms of, let's say, importance, not in any kind of, order. Maybe this will be used more. I don't know really, but this tends to be more of a typical topic of 477 than this. It should be both. So let me cover these two first, right, and then this last. But that doesn't, I don't know. It doesn't mean that these are more important than those anyway. But so law of large number. So we said this before, right? Both of these has to do with the idea that if you have x1, you have a sequence of ID random variables. Okay, and you don't care. The beautiful thing here is that you don't care about whatever the distribution is. Meaning that you only need them to have some variance and some mean. All right. And by the way, these are not automatically true, because you have seen random variable that has no mean, or infinite mean, or infinite variance, right? So those will not be satisfied in this requirement. But as long as you have the first and second moment, you don't care whether it's uniform, exponential, binomial, whatever, right? They all fit into this framework. Then law of large number says, right? So let's define this guy called x bar, which is the sample mean, right? Sample average, right? Because law of large numbers, there are different ways to look at law of large number central limit theorem. One way, which is the statistical way, is to say that, to see that they kind of give you behavior of x bar in general as n goes to infinity. The law of large number says that x bar would goes to mu, and let's just maybe say this. Oh, okay, hold on. As n goes to infinity is equal to 1. Okay, so that's law of large number. So notice that a lot of times you will only see this, which is whatever, right? This is how people tend to write that casually. But technically speaking, that's not vector x, is x bar. X bar is a random variable. So x bar conversion to mu is a random event. All right, a random variable conversion to a number is a random event. So you have to put a probability on it. The fact that the probability is 1 is exactly a good reason, a good thing, meaning it's guaranteed that this converges. But still, that doesn't mean you can just neglect the probability, whatever, right? But if you find that a little bit too technical, this would at least fly, right? Under not super rigorous environment. Okay. So basically it says that the sample average is very close to the population average, population mean, right? As n goes to infinity, as sample size gets large. The central limit theorem will tell you, so this will tell you sort of like the value, right, of the sample average. Central limit theorem will tell you how far, right, the error will be. So here we have to, so this is not a rigorous statement. The rigorous statement will be probability x bar minus mu over sigma over root n is less than x will converge to, I think we use this notation, no? Phi of x, right? The CDF of the standard normal. As n goes to infinity. So let me explain, right, why this is not a rigorous statement and why this is. This is not a rigorous statement because this is a random variable. But this guy right here is not anything. It's just a model, right? Random variable has values. A model has no value. So when you say this converges to a standard normal, is kind of vague mathematically. But I guess we all know what that means. And what that means is, of course, this. Meaning that when you want to measure the probability, right, of this guy being in some range of values, in particular less than x, let's throw equal here, doesn't hurt anything, then it will be roughly the standard normal, less than or equal to x, the CF standard normal. So that's what we mean. Okay, so that's a rigorous statement. Same as this is a rigorous statement, but if without it, right, you're fine. So again, right, the meaning of this is that on average, the sample average will be very close to the true average. But if you care to specify how far it is away from the true average, then that's the chance, okay? Now, there are tons and tons of ways, right, for central limit theorem and Laplace-Learn to be used. The application is a lot. But let me tell you, right, the applications in terms of statistics, and just some, right, you will see this in parametric stats, right? Point estimator. So in statistics, right, there's the idea called unbiased estimator. So first of all, maybe let's backtrack, right, and say what is an estimator. An estimator basically is just any function of the sample that's used to estimate a parameter. So if you use the sample and you declare that you want to use that to estimate some parameter, that's an estimator. So in this sense, routinely the sample average is, so hat here is basically the statistical notation to say that's an estimator, right? A sample average is used to estimate the population average, right? So here you think mu as unknown, as hidden, and you're trying to estimate mu based on the sample average, and you want to ask how accurate that is. So an unbiased estimator would say that the expectation of the estimator would be the true average, right? So, well, I guess so maybe I'm not saying the right thing here, because I think it should be a consistent estimator, not an unbiased estimator. I think it's a consistent estimator. So anyway, so maybe let me just scrap that definition even. But so yeah, let's backtrack and say that the estimator, right, the sample average is used to estimate the population average. And you wonder how good this will be, right? How good is X bar as a mu hat? Well, the reason is this, right? That the sample average doesn't have to be the only estimator for the population average. It may seem the most obvious one, and it turns out to be the best one anyway, but there are other ones. Let's say at least, maybe the sample median could be used as an estimator for the population average. Again, sounds a bit weird, and there's a reason why it's weird, but just in terms of throwing out ideas, it's hard to see why one is better than the other. But here, for example, right, first of all, the Laplace number definitively point out that this is a good one, because as if you have a large enough sample, then let's just use a casual notation that if you compute the sample average for a large sample size, then you can be confident that it's approximately the true population average, population mean. Okay, but of course, this approximation entails some error, right? And the error comes from the randomness, right, of each of the measure, if you will, right? If you think of this as a true measurement, whatever that is, and each of this is a trial, each of them, then each of the trial has some error, right, around the true mean, the true number. But when you form the sample average, you still commit some error. How large is that error, or what's the probability that you commit some kind of error? Then there's a notion called the confidence interval, right? Let's say 95% confidence interval. What does that mean? A confidence interval, right, is something that requires, so basically it will be formed, let's say, using a left estimator and a right estimator, right? The hat here means that they both are from the sample themselves, such that the probability that the true average, the true mean, is in this random interval is equal to 1 minus alpha. So it's equal to 95%. Okay. So the challenge is to find, right, two random quantities or two sample dependent quantities such that this unknown quantity belonging to the sample data, sample estimator in this range is 95%. All right, that's a challenge. Now, you may, right, have seen, so here let's assume that sigma is known, because if sigma is unknown, then we need to throw in the sample variance, sample standard deviation, which is like something we don't need to go into. Suppose that sample populations, suppose that the population standard deviation is known. Then many of you might have seen, right, that the left and the right bound, right, for the confidence interval will be x bar plus minus, right, z, hold on, x bar z 0.05 times sigma over so whatever. Okay. So first of all, let's try to explain what this means. Z 0.05 is the percentile such that should I call it Z95? I think people call it 0.05, which means that they're 0.05% above it or 95% below it, right? So it's just a quantile. This is a known number, right? Such that 95% of the standard normal is above it, or 95% of the standard normal is below it, right? And so basically, this is a quantity that is like completely, right, formed or known by the sample, right? X bar is a sample average. Z 0.05 is a sample quantile. Oh, sorry, is the normal quantile. And then sigma is a population, right? Standard deviation. Root n is a sample average. Sorry, sample size. the question, right, is why, if you form this, right, which is, let's say, a reasonable quantity, why is it that probability that this number, which is an unknown number, belonging to this interval, which is, right, really a way to say this, probability that x bar minus z.05 times sigma root n less than mu less than x bar plus z.05 times sigma root n, why it must be 95%. Oh, and by the way, right, I think I made a mistake. If I do z.05, then it should be 90% confidence interval, because there's a two sides I'm forming right now. So 90%. So y must be 90%. Right. And as you can see, right, well, this will be the same as probability, right? That x bar minus mu over sigma root n in terms of absolute value is less than z.05, right? And the point, though, is that this guy right here, if the sample comes from some unspecified distribution, or from some, let's say, some non-normal distribution, let's say uniform or binomial, whatever, right? Then when you form these quantities, the x bar or this is not normal. And so you have no reason to say that this will be 90%. No, none, whatever, right? Especially when n is small. And so in some way, right, people will still form this anyway because they have nothing better to do. But this should not or may not be 90%, and this is probably called the abuse of central limit theorem in some way. Because basically, so first of all, right, what do people have in mind when they quote this? They have in mind that asymptotically, this is normal. But notice this is converging as n goes to infinity. So you need a large sample. But if you have a large enough sample, then this number is approximately 90%. So you could wave your hand and say it's 90%. So this is true, but this is called an asymptotic confidence interval, right? This is roughly true, but it cannot be true when n is small. So I guess I go into some tangents here, but the point is, right, central limit theorem is invoked as n goes to infinity to help you conclude that yes, these left and right bounds are the right confidence intervals, one of the choices that allow you to make sure that the true population mean being in it is some specified probability like 90%. All right, but without a central limit theorem, you will be stuck trying to determine what the distribution of the sample average is. And if you have kind of some inkling on the sum, right, of random variables that we looked at in this class, you'll see that it's not a very pleasant thing to look at. I mean, in general, right? Because the sum could be pretty complex to figure out. So that's one very common application that everyone will see, right, given the state of the art these days, in terms of law of large number and central limit theorem, right? But they have many applications, right, beyond this context. But let's say that the way that it's used is similar. Okay. And yeah, if we want to do more about this one, then we need to do some problems. But like I said, right, we just want to kind of expose you to this materials. So we'll skip the problems for now, unless you have some questions. So yeah, any clarifications for this stuff? So actually, right, in terms of this, I like to offer at least some intuition or some proof on why this is true, because maybe that, who knows, some students might be curious, right? Because actually you should really question, because these are really amazing results, right? You do not say what the distribution is, then why is it that the sample average always go to the mean? And why is it that the standardized, right, ratio like this, or the z transformation, right, of the ratio like this always converge to a standard model? So the reason why I put the proof here in bracket, right, is because you can be, it's not meant to be rigorous, right, but it'll give you some idea. So the first thing, right, that's easy to see with the X bar is the following, right? The expectation of X bar is expectation of sum of xi over n, I from 1 to n, which is 1 over n sum of expectation of xi. Right? Which is 1 over n times n mu, which is mu. And variance of X bar is variance of the sum, right? Which is 1 over n squared, the sum of the variance. The reason why we can do this without the covariance terms is because they're independent, right? The xi is independent. So this will be 1 over n squared, n sigma squared, which is sigma squared over n. And so you see that X bar is such that expectation of X bar stays constant, but the variance of X bar converges to 0 as n goes to infinity. And if you just contemplate on that, right, a random variable with constant expectation but variance going to 0 must be approximately that constant. So that's Laplace number for you, but it's not quite right. Because in advanced probability, we talk about the sense of we call it sense of conversions. Yeah, right. Different ways you can define conversions. And here, what we just proved, or what we just explained, is in more advanced probability, it's called conversions in mean square. All right. But the Laplace number proper is conversions. This is called almost surely. So almost surely and conversion mean square are two different senses. So this may not be enough to get you to conversion almost surely, or you can prove, this implies the other one by some mean. But either way, what I'm saying is like this gives you one clue, but it may not be, how to say, the exact sense that the Laplace number writes down. It's just an easy thing to look at. Now, when it comes to central limit theorem, right, then the way to do it is as follow, right? So X bar minus mu over sigma over root n. First of all, let's take a look at this. If you look at this, right, what do I want to say here? This is sum of xi over n, right, minus mu divided by sigma over root n, right? So if we multiply by n on both sides, so this is xi minus mu in parentheses, right? And then I think multiply by root n over sigma, right? If we multiply by n here, sorry, over root n sigma, I think. Right, 1 to n. Okay. So what I want to say is this, right? If I look at just this alone, what this is, right, is it's going to be a random variable with mean 0 and variance 1. So I could just look at central limit theorem in this following version. Let xi be iid with mean 0 and variance 1. So I throw away the mu and sigma square because they just kind of, a scale version. Then the sum, right, of xi over root n, the probability of that less than or equal to x converge to standard normal as n goes to infinity, right? So that's one simplification. Now, of course, the advantage of this is the probability of xi less than or equal to root n times x, right? Because I can multiply both sides by root n. Okay. And to investigate this, right? Remember, this is about distribution of a sum. And remember, the MGF is a nice thing to look at here, right? So here, let me switch notation to M, right? Because phi has been used to denote the CF. So if there's the MGF of the sum, right, is the product, right, of the MGF, right? Which is, you know what? Sorry, I think I still want to keep it over root n here. Sorry. So I don't think I need this statement. Sorry. The MGF of the sum, right, is a product of the MGF. Okay. Which is, right, because these are independent, it will be just the MGF of one of them raised to n power. Okay. Now, let me try to think here. Right. So here, probably I will need to look at each of the xi's xi over root n. Okay. So what do I want here? Let me do this. Sum of xi over root n, xi over root n, over root n. That's a scale factor here that's still carried, right? Now, if you remember, right, the MGF has a following property, right? If the derivative of the MGF, right, and if you plug in t equal to 0, gives you the expectation of it raised to n power, right? So maybe let me change it to k because we have used n. So basically, if you differentiate, you get the moments. So, but what that means, right, is I can expand the MGF around t equal to 0 using Taylor expansion. Right. So the value, right, of the MGF, so here the expansion is as follows, right? Second degree Taylor expansion. Second order Taylor expansion. Says that f sub x around x equal to 0 is approximately f of 0 plus f prime of 0 times x plus the second derivative over 2 times x squared. Okay. So, or, okay, it's f of t, right? And this is t. and this is t squared. Okay. So where f of t is what I have in mind with the MGF of x1 over root n, okay? So when you plug in t equal to 0, then the MGF, right, of any random variable is expectation of e to tx. Therefore, the MGF evaluated at 0 is 1, right? So this guy is approximately 1 plus, right? The xi has mean 0 variance 1. So xi over root n also has mean 0 and variance 1. So f prime here, right, is the first mean. So it's 0. So there's no first term. Xi has mean variance 1, but if you divide by root n, that has variance 1 over n, right? And this is really the second moment, but because this first moment is 0, then the second moment is equal to the variance. So this is 1 over n. So it's really t over 2n raised to n power. But if you check, right, yeah, if you check, right, this will converge to e to t over 2, right, which is exactly the MGF of a standard normal. Am I right? Oh, sorry. T squared, right? Because this is t squared. So e to t squared over 2 is the MGF of a normal, right? Remember, right, the MGF of a normal mu sigma squared is e to t mu plus 1/2 t squared sigma squared. So e t squared over 2 is MGF of normal 0, 1. So either way, right, this is quite maybe, right, a lot of math going on here for you. There's some sort of like standardization. And then, right, there's the MGF technique, and then there's the Taylor expansion. But if you can chase all of this, right, you can see that basically the result is quite natural. And the key though, right, is that basically when it comes to the MGF, right, which is the main tool used here, the first 2 or first 3 terms are the same regardless of the distribution, as long as the mean are the same and the variance are the same. But the higher terms would disappear with higher n. So that's why, right, all distribution will converge to e to t squared over 2, meaning it's standard normal. All right. Okay, so probably again, this is offered for those of you who are interested in why central limit theorem works. But if you know you're not super interested in these things, that's okay. All right, any question? All right, so that's enough about law of large number and central limit theorem. The last thing I want to tell you is about conditional expectation. And let's say conditional variance. Which is a very common technique used in probability to calculate expectation variance. So this one is by far way more popular, which is that the double expectation, right, gives you the original expectation. It's called, yeah, some circle called log double expectation, right? If you condition and then you take expectation, then it gives you the original expectation. So what does this mean to begin with? What this means, right, is that when you condition X condition on Y, and you take expectation, this right here is a random variable in terms of y. And if you take expectation again, then you average out the y, then you get back the x. Okay. So first of all, let's see why this works in terms of, let's say, a simple proof. Proof, right, using CDF, using PDF. So expectation of x given y, right, is the integral of x times the density, conditional density of x given y, divided by the density of y. Right? Sorry, dx. So you see, after you integrate this out, this is a function of y. And so when you take expectation of the conditional expectation, then you take this function of y, you multiply it with the density of y, right? And you integrate out. Sorry, this is not f of x given y. This is the joint of x, y, sorry. Right, which is the conditional one. And you see that if you look at, right, this integral, this can be brought in, right, because it's a constant, in terms of x. So it can be brought in and then cancel. Then the integral really will be the double integral of x, f x y, and it's not x given y, but it's just x y. Dx dy. And this is exactly just the expression of expectation of x. Okay. So that's the proof of why the law of double expectation works. Now, as in terms of the use, right? Let's show you a calculation to compute, let's say, expectation of x, where x is a geometric random variable. Well, we know the answer, right, is 1 over p. But using a sum, right? Let's see how we can do it using conditional expectation. So what we will condition on is the first toss. So it'll be 1 if the first trial is true, first trial is successful, and 0 otherwise. Right. So remember, right, a geometric is a number of trials until the first success. And we'll look at the result of the first trial. So what is x condition on y? So x condition on y equals to 1, right? Clearly will be 1. Because if the first trial is a success, the number of trials to see the first success is 1. But x condition y equals to 0 will be what? And this is the classical move when you do double expectation. If you see something, then basically the experiment repeats itself. If the first trial is a failure, then you waste 1 time because you waste 1 trial. And then basically you can think of it as you just restart. the geometric, right? If the first trial is a failure, then that wastes you one chance, right? One trial. But the remaining one, you still search for the first success anyway. So these are called the X tilde, which is Y tilde. Tilde is because it's also a geometric P. So it has the same expectation X. So it's kind of repeating the trial, repeating the experiment. But it's not the same value as X, because clearly, right, X is the whole thing here, and X tilde is only this part. And only when this is a failure, right? So we call it X tilde. But X tilde is still a geometric P. All right. And so when you combine these together, you have something like this. Expectation of X conditional Y equals to 1 is 1. Okay, it's a constant. Expectation of X conditional Y equal to 0 is 1 plus expectation of X. Because, X tilde and X are the same thing, right? And why do we leave it as expectation of X? Because we're pretending that we do not know this, and we're trying to solve for it. So we just write expectation of X here. Okay. And now we use the law of double expectation. So expectation of X is expectation of X given Y. And now you see this is a function of Y. So we will multiply these values with the probability that Y being a success or failure. So this will be 1 with probability P. It will be 1 plus expectation of X with probability 1 minus P. So what turns out then is our analysis gives us a equation in terms of E of X, right? And you see that if you bring this over here, 1 minus P is just P. And then P plus 1 minus P is equal to 1. And therefore, expectation of X is 1 over P. So again, right? I mean, this is done to expose you or introduce you to, right, conditional expectation, which is something like, in, say, stochastic process, we spend a lot of time studying and working with. But right now, right, I just want to kind of show you the idea, because this technique is very, very powerful and very common in solving certain kind of problems that have a convenient variable that you can condition on. All right, so any question? All right, so I think this, I know we'll still have like 5 minutes left, but I guess, so the final exam, right, is on Wednesday. It's cumulative, but study your homework. It should be the best way to prepare for the exam. In terms of materials, like in terms of the how the materials are spread out, I'll try to make it uniform across all chapters, but there's no promise there. The reason is, right, if a material is more complex, let's say, I don't know, joint distribution or something, right, there will be more questions that can be asked about that topic. But if a material is, simple, let's say, I don't know, basic probabilities, there are not as many questions, right, that can be asked. So the materials won't be focused, right, on just a topic. I don't know, like say transformation of variables, right? The Jacobian won't be like that. So, but on the other hand, right? I mean, like I said, the later chapters will be more complex, so there might be more questions toward that end. Who knows? But overall, right? It should be roughly uniformly distributed, whatever that means, right? So otherwise, like I said, study your homework, make sure you know all the things there. You should be fine. Okay. Any question before we, I guess, finish our lectures? All right. If not, I guess let's finish 5 minutes early today, right? And well, have a good semester, fall semester, right? If I don't see you around.
Thank you.
Sure.
Thank you.
Yep. Thanks.
Oh, um,
Yeah.
I have a quick question. I don't know if you mentioned it before, but how many like note sheets are we allowed for the final?
Same. It's still
Same.
two-sided,
Oh, just
two
okay,
page.
just one.
So one,
Oh,
one page, two-sided.
One
Yeah.
page. Okay. All right. Thank you.
Hey, I had a question about a problem from chapter 6 in the textbook.
Yeah. Which one?
Okay, do you mind if I screen share? Because I have it like screenshotted.
Okay. Sure.
Okay. Okay. So it's example 2F. They define the first joint density function and they say that the two variables are independent, which I understand because they're using the theorem where you can like factor it,
Example 2F here.
right? Yeah,
If the joint is equal to 0, are the random variables independent? So the first question then, yeah, they're independent, yes. Mhm.
yeah. The first one I understand because you can like factor it, but the second one, they say it's not independent because they define it in their function I of xy.
Yeah.
And I don't really get why can't they do the same thing on the first one? Like I get that the second one has more restrictions on the domains of x and y, but the first one also had the restriction that x has to be between 0 and infinity, and so does y.
No, but that's the whole point. That's how they try to explain the idea in terms of interior function. But right, as I explained before, the range of values are very important. The first one, x and y, have no interaction in terms of domain. X just goes from 0 to infinity,
Okay.
y just goes from 0 to infinity. The second one, if you look at it carefully, it says something like x is less than minus y or something like that. Right? Minus y is
Right.
less than x, less than y. So if x is always bound between minus y and y, they clearly should not be independent. Agree?
Okay. Okay,
Now,
I understand. Yeah.
now the like I said, the number one test, you can use the interior function. I don't like it though. You can, but it's more of an idea you can see in statistics. Right now in this class, what you can do, if you want, is calculate the marginals of x and y.
Right. Okay.
And if you calculate the marginals, you will see immediately you have to use a region, right, that they specify. And if you use that
Okay.
region, then when you multiply those marginals together, you will not get the joint. Right. So you see,
Okay.
when you say that the joint splits, it's just a waving hand to say that, well, they will split into the marginals. But how do you know? Did you calculate the marginals yet? Usually, if the bound are independent of each other, then the marginals are exactly how the split works, right? But in general, if the region
Okay.
interacts, then the marginals are not how the split looks like because of the limits, right, involving the x and y. Do you understand?
Yeah. Yeah. No, I see how that would like work out.
Mhm.
Okay. All right. Thank you so much.
Sure. All right.
Okay. All right. Have a good one.
All right. See you. Mhm.